Good afternoon to all of you. We are almost at the last part of the this quantum mechanics for this semester. We are going to talk about this. With respect to the translational motion, the particle in a box, we have the last part that is known as tunneling. And because it is a quantum mechanical phenomena, we call it quantum tunneling. So the situation in a particle in a box was that you had high energy walls. The energy was rising up to infinity at the walls, at both the ends, the bordering points. And inside the you had potential energy was zero, only kinetic energy. And then on the other two sides you had potential energy rising to infinity. Now what will happen if the potential is high but it is not infinity? Uh, so so that kind of situation we are now going to imagine, we are going to understand. So what if there is if the ball is trapped but the walls are not have sufficient energy, it is not rising up to infinity, then what can happen? So that kind of situation we are going to imagine, we are going to work out. So it can be compared to a situation where you have set a ball rolling. So from classical mechanical point of view, if the ball is rolling like this, it can cross over to this mountain, this one, if only if it has sufficient energy E. If E is greater than the potential barrier V, so potential energy is represented by V. So at here, when the ball is here, this is the potential energy. So when the ball is rolling, it has energy. So see the direction, it is going like this. It must have sufficient energy E, which is greater than the potential energy V. So this is what we call as a barrier. This is a potential barrier. This hill that you are seeing is a potential barrier, and it will be crossed. The ball will appear on the other side only if it has sufficient energy, and that is E is greater than V. The potential then it appears on the other side. This is the classical picture. But what can happen in quantum mechanics? So suppose this ball is nothing but electron. If so, a particle like electron, and then we are trying to cross a barrier. Can it energy barrier? Is it necessary for the particle that if we want the electron to appear on the other side of the hill, is it necessary to have the energy greater than V? Potential barrier is V. This is V. No. Even if it has less energy, quantum mechanics allows the particle can still pass through like this. This is what we know as tunneling. So if you construct a tunnel, you can without making much effort, uh, you can pass through. So this kind of thing we can imagine. If you without having sufficient energy to cross over the hill, one makes a tunnel and can pass through. So this kind of thing happens in quantum mechanics for such particles that we are talking about, electrons and others, protons, anything like that. So these subatomic particles do show this kind of behavior where the the barrier that is created, uh, potential barrier, even if the energy of the particle is less than classically expected, from classically expected point of view, if even if the energy is less than the potential barrier, it can still appear on the other side. So that is defined as tunneling. So which is unimaginable in from classical point of view. In a classical mechanics, you can't imagine this happening. So this is a classical simple in 11th 12th classes you must have heard about conservation of energy, and based on that the first picture was is taught like that ball. So what happens when the ball is so so this kind of behavior, again it is cutting through this. Just a moment, can I try this? So what it means that it can, so what we say that in it is not expected, but if it in quantum mechanical, for particles such as electrons, it is still possible, and you can see sometimes that, so we say that the ball can tunnel through the barrier on and appear on the other side even if the kinetic energy is less than uh, the required thing. So this is now what we are expecting. We have oscillations. This is the wave function for the particle executing motion before the barrier, and the barrier on the it it hits the barrier on the right hand side. The potential of the potential energy is V. It is not infinity. That's what I'm telling. So, and the E is the energy with the particle. This smaller arrow that you are seeing is less than the V. So what will happen then? The wave function that you are seeing, it has high amplitude here, hits the wall, and within the wall it is going through with a dampening, reducing amplitude. The amplitude is going down, and finally it comes out of the barrier and again starts oscillating. So within the barrier it is not showing a sinusoidal oscillations. It is only showing a decay, an exponential decay of the amplitude. So there's kind of a resistance, you can say. There's a obstruction to its oscillatory motion, and the amplitude, which was whatever it was at the when it enters the barrier, when it hits the barrier, it can go down from this and finally come out appear on the other side. चौथी क्लास कौन नहीं, उनकी तबीयत ठीक नहीं है। हाँ, इसीलिए आज तो so you can see what I am saying. So decrease in amplitude from here to here, it is inside the barrier. This is the barrier. Inside the barrier, what we are seeing a decrease in the amplitude along this path. This is the decrease in amplitude, and by the time it comes out, appears on the other side of the barrier, uh, the amplitude has decreased. You can see this है वहाँ पे आप ले so the barrier after coming out of the barrier, so the so to a great extent the amplitude has decreased, and with this that same amplitude it starts oscillating on the other side. Okay, so oscillation before the barrier, hits the barrier, amplitude decreases, you see an exponential decline, and comes out with a barrier with a reduced amplitude, keeps on oscillating on the right hand side. So this is what is likely to happen if the wall has a finite thickness and it has finite potential energy. V is not infinite in this finite potential energy. and finite length of the barrier, then we can describe the wave. Something like this may happen. It will not abruptly decay to zero. So in that, so what we were seeing earlier. यार तो पहले बोलना था, कितनी देर हो गई? मेरा म्यूट है क्या? नहीं, म्यूट तो नहीं है। ओके 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 ओके। अच्छा, कनेक्टेड तो है। नहीं तो अपना एयरटेल पे ही लगाना पड़ेगा। हम्म, कोशिश करता हूँ। थोड़ा सा रुक जा। Just a moment, I am trying to connect with my mobile phone because looks like the recording हो रही है ना? हाँ, looks like that this is not working. कहाँ गया मेरा? Let me change. Okay, अब आ रही है आवाज? हेलो, ठीक है। चलिए, अपने मोबाइल के भरोसे ही होगा। Okay, so particle in a box, you have amplitude like this. Particle comes at the on towards the this side, hits the wall, and the wall has doesn't have infinite energy. Potential energy is not infinite at the walls, so the amplitude does not decay to zero. It will slowly decay as it passes through the barrier, comes out of the barrier. Now the amplitude has been already reduced, and that with that reduced amplitude it keeps on oscillating. So देखिए, छोटे से oscillation के साथ sinusoidal oscillation right hand side में दिख रहा है. So this appearance of something, so you can, first observation, wave function does not will not decay abruptly to zero at the walls if the potential is not infinite. So, and if it is what we have imagined here, the wall is thin enough, then you can think of this coming out and perform oscillation in the same way as it was doing on the left hand side of the barrier. The on the right side, when it comes out on the right side, it can still perform the oscillation. So you are visualizing the particle as a wave, and this is what happens. So in another sense, the particle, some part of the particle is appearing on the other side. Okay, the particle appears on the other side, with maybe reduced velocity, motion, something like that. So that is, that kind of thing can visualize. We are talking about translational motion when it was trapped in a box, and the walls of the box doesn't have infinite energy, potential energy at that, and then you have this kind of thing that happens. And so Then outside the box we have to, what so this is something that was unimaginable in classical mechanics, that if उतनी एनर्जी नहीं है, दीवार तोड़ने की एनर्जी नहीं है, लेकिन दीवार के पार निकल के आ रहा है, ठीक है, तो ऐसा कुछ हो रहा है. Although it has insufficient energy to escape, it can still uh, be expected to be other side. So this is what you are seeing. This is a kind of leakage happening. So this leakage that you are seeing in a classically forbidden region is called tunneling. Okay. So now we can start analyzing. So we have three parts that we can write Schrodinger equation for three parts. First part on uh, so from the take the barrier as your reference point. So left hand side of the barrier and right hand side of the barrier, and then in the barrier. So three parts are there, and each of them will be to describe the motion. We have to write Schrodinger equation for all of them, and for the so taking barrier as your reference point, so left side of the barrier, left of the barrier, x will be negative. So when we start thinking, so this is x, we start 0 and L, so this is length of the barrier. What we are referring to here, it is in reference to the length of the barrier. So our discussion, so this is from this, so left of the barrier, x is less than 0, so x negative on this side, x will be negative on this side, and on this side it is positive, greater than L, less than 0. So these are the two things that we are considering. So x is less than 0, uh, and the v is equal to 0. So that was a particle trapped in a box. We have already discussed that potential energy is 0 inside the box, and so we can write the same equation as we had learnt earlier for the particle in a box. And for that you can expect that this kh cross, it is a simple thing, we had find that momentum was kh cross, or which is equal to 2m under root 2me kinetic energy. Simple. So you have k square h cross square by 2m is kinetic energy. So in other way you can write it. So this is what we get. Kh cross is equal to under root 2me. So this is to the left of the barrier. This is the point that we are making. Now an equation is this, which we have already derived in previous cases. Now inside the barrier, 0 to L, within the barrier. So we are talking about something within the barrier, within the wall, within the wall or within the barrier that we are talking about, 0 to L. So length of the wall is capital L, starting point of the wall is 0, and to the right hand side where it ends, the wall ends, that is capital L. So the potential is not rising to 0, it is finite. So we write V here. The particle is moving through the barrier with having a potential energy V. Then this is the equation that we can write for the second part within the barrier. And we have already assumed that, which is classically forbidden from so energy, kinetic energy is less than the potential of the wall. So that, imagining that kind of situation, we can write it doesn't have sufficient energy to cross the barrier. V is less than V, so E is less than V, and so V minus E must be positive. This is must be positive. So the general solution for this kind of equation will be something as if C. So the C, because we have already mentioned A and B as the coefficient for the first part of the motion, the second part of the motion within the barrier would be having coefficient C and D, and two exponential term. One is kx. So this is kappa, this is not k we have already used over here, k, so we are changing the symbol to kappa kx, and this is the way we can write for the wave that is appearing over there. And if we are writing it like this, then the energy as we have described is v minus e. So v minus e has to be taken, so the momentum would be equal to this. Instead of e, now you have v minus e, which will come into picture, and that is the kh cross. So this is the situation that we are having. It is moving and hits the wall, then there's decay in amplitude, so exponentially decay of the amplitude that we can see, and then comes out of the wall, oscillates with a smaller amplitude. So on the both side the condition is same, E is greater than V, and in the walls you have energy less than V. So now taking the case within the barrier we were discussing, so it was V kh cross was 2m V minus E. So we have clearly seen that C, so this is the equation that is inside the barrier, we can imagine, because it is a decaying function. It is not, remember, within the wall it is a decaying function. Yes. किस चीज का है? ओ अच्छा, ये अपलोड करना है जी सर, ओके, थैंक यू। सो क्या कह रहा था? Yes, so what we are seeing that the wave function oscillating function here on the right hand side also it is oscillating function, but within the wall, so look at this part, decaying function within the wall, within the barrier, it will be constantly decaying, amplitude घटता जाएगा, कम होता जाएगा, decaying function है. So nature of function is different. So one thing mathematics आपको यहाँ से guidance मिलता है, observing the nature of motion that is happening. जब वॉल के अंदर चला गया है, सिर्फ ये ऑसिलेट नहीं करेगा, इसका एम्पलीट्यूड घटता, जितने एम्पलीट्यूड पे वो एंटर किया था उतने से कम होता जाएगा, और फाइनली अगर वॉल थिन है तो बाहर निकल जाएगा. अगर वॉल काफ़ी थिक होगा, इफ़ यू एक्सटेंड द थिकनेस एंड द डिकेइंग फंक्शन गोज, तो हो सकता है कि वो फिर वॉल के अंदर ही फंसा रह जाए, जीरो हो जाएगा वॉल के अंदर. सो दिस इज अ केस वी आर डिस्कसिंग फॉर अ थिन वॉल वेयर डिके होता है लेकिन कंप्लीटली जीरो नहीं हो पा रहा है. ओके, सो but so this is the situation that we are imagining, and so for decaying, writing a decaying function, general type function mathematically, it is of this nature: e to the power k kappa x, e to the power minus kappa x. Remember, you can see notice one more thing, the I is gone, no term of I, the imaginary function is gone. It is a real function that we are writing for the barrier, inside the barrier. So so the nature of function that we are writing inside the wall is different from the left hand side of the barrier, where it was oscillating, on the right hand side of the barrier where it was also oscillating function. Okay, so the nature of that changes, and that's it is also to be noted that it has become it is not a complex function on in when we are writing inside the barrier. So if the energy is if you had sufficient energy greater than the potential energy, in that event it would still have been oscillating conditions. But we are not. We are talking about here when you have on the left hand side v was 0, on the right hand side v is 0, and within the barrier v is finite v. So to the right of right side of the barrier v is 0 again, left side already 0 है, और अभी जो सिचुएशन हमने इमेजिन किया है E is less than V inside the barrier. So in that situation it is a constantly decaying function that you will see, and the function that we are representing was, so the right hand side we also note the right hand side the function will be same, similar nature as the on the left hand side of the barrier, but of course the amplitude will be reduced, and so we will have a prime and b prime we are writing to indicate that. And here again the nature of equation, so it is only the coefficients have changed, but rest of the things e to the power I kx, e to the power minus kx, that will remain. So it is a nature, this is an oscillating function that we are writing. Oscillating function has uh, it is a complex number. It is a, so it is complex when you were, and the previous case when you were writing this is uh, not an oscillating function. If it is not an oscillating function, only a decaying function, there is no, the function is not complex. Not an oscillating function. This is not an oscillating function. It is not complex. It is not a complex number. Okay, so oscillating, it will be a complex number represented by having a component of I kx, I e to the power I kx, e to the power minus kx, something like this must be there if it is an oscillating function. So the complete wave function for particle incident from the left, and if we are trying to write, so we have three sections that we are, so we are looking at a wave that was before hitting the barrier, the incident wave. The wave is incident upon the barrier, first time it is hitting the barrier. So a portion of that wave will be reflected back, we have not yet considered this part, and a portion of that wave goes inside the barrier and with a decaying amplitude. And after, if the wall is thin, once it comes out of the barrier and with a reduced amplitude and continues its oscillation. After that it has tunneled through successfully. So this is what we have seen in the picture in the previous slide. So so now there are few things that we can make out to understand this. The function must be continuous at the barrier. So barrier का दो position है. X is equal to 0, the barrier starts. X is equal to L, the barrier ends. So within the barrier, so at the point of it is hitting the barrier, so that is, the function has to be continuous. Imagine this way. So what we are talking about is the wave is traveling and it is hitting the wall. So this big purple colored thing that you are seeing is the wave, amplitude of the wave is being shown in through different way, and a part of it is reflected. So this arrow that you are seeing, the green on the to the left hand side, this is a reflected wave, and some of this is with a decay in amplitude, some of this is coming out, and oscillating with the same reduced amplitude. So reduced amplitude coming out with the reduced amplitude, then oscillates like this. Okay, so this is the transmitted wave. So this is the picture that we have. It is a weak, very weak signal. It is a weak wave, you can say, reduced amplitude, with reduced amplitude, as compared to the motion on the right hand side before hitting the wave. Okay, so this is the component that we are visualizing, and we will see that this a plus b and the components that we are talking about must be equal to c and d. So the equation, okay, so just you are having, so first equation describes the wave uh, when it hits the, before hitting the wall. Okay, so at the point juncture it hits the wall, the function has to be continuous. So this is a zoomed in view of the hitting the wall. So the function has to be continuous at this point where it is hit. So that means the equation first of oscillating nature and equation 2, that the wave function for the decaying function, both must be equal. Psi, the wave function here, psi 1, the oscillating, when it hits at this point, both function of the left hand side, right hand side must be equal. So that is to maintain the continuity. And similarly we will analyze so we have written equations like so here it was psi is equal to a to the power e I k x plus b e to the power minus I k x. Inside the barrier we are writing psi is equal to e to the power c e to the power kappa x plus d e to the power minus kappa x. And finally, so this is so region 1, this is region 2 in the barrier, inside barrier, and third that we have written after it's on this side, outside the right hand side of the barrier, left hand side of barrier, and on the right hand side of the barrier it will, we are describing it as psi being equal to a prime e to the power ikx plus b prime e to the power minus ikx. So what I am saying is that at the point it is hitting the wall, first point where it hits the wall, left hand side, look at this, x is equal to 0, at x is equal to 0, and this is x is equal to L. So at this point these two functions must be equal, and the other end where this is exiting the wall, when it is moving coming out of the wall, here the two functions at this particular point, if you are considering, so consider this point where it is hitting. Now at this point this function and this function, these two functions must be equal, only then तभी तो continuity बनी रहेगी. You have to, the functions, all the function that we are describing must be continuous. So, and they will be continuous if the two functions are equal where they hit the wall or they exit the wall. So we are going to equate it and find the values, what A, B, C, D should look like. Okay, so this is the boundary conditions that we have identified at the two ends of the barrier. The three functions that we have written, they two of them must be equal to each other. Okay, so then only Schrodinger equation will be valid for all of them. Uh, so to find the coefficients, we will be working out in this one. Function must be continuous. So apply this at the start of the barrier. This function should be equal to the function which we are expressing as this. And so we put the value of x, substitute the value of x. So x is 0. X is 0 here. You can see this. So when you put e to the power 0 is equal to 1. So 1, 1, you write that. So a plus b must be equal to c plus d. This is an essential requirement that we have just found, that the if the function are continuous, then psi must be equal from both. If we are looking at the decaying function within the wall, or we are looking at oscillating function on the left hand side of the wall. Okay, so both function must be. Similarly, you apply the same thing to the end of the barrier when x is equal to capital L. Then again, this function inside the barrier should be equal to this function which is outside the right hand side of the barrier. It is coming out, and then you substitute the value of x, put L like this. So if you do that, and then we also realize that first derivative of the function for the Schrodinger equation to be valid, first derivative of the function must be continuous. So function will also have to follow this thing. So so if you do this, the first you do the first derivative thing. So take the first derivative, d psi by dx, they should be equal. So d psi by dx is equal, then that means both of them. So we apply this thing over here to simplify. So at x is equal to 0. So again, this is, we are getting another equation like this. So this gives us ika equal minus ikb is equal to k kappa c minus kappa d. So the same thing we can also apply to the other side, where the wave the ball is making an exit, it is coming out of the barrier. The So in that case, again take the derivative, first derivative, when it is at the, so length x is equal to capital L, end of the barrier, apply this. So we are writing the first derivative of each component that is there, and this is the second equation that we are getting. So again the four equations. First we have got a plus b is equal to c plus d. Second, we got consideration of the first two, uh, the function has to be continuous. This gives me two things. This is for functions are continuous. So this requirement making is giving us two functions. These two functions, the slope d psi by dx must be continuous. This is by applying this, we are getting another two equation. So there are four equations that we are getting, and so so using this we can probably simplify it further. uh, so if you throw the ball towards the barrier from the left hand side, so left to right, there can be So if the ball is thrown towards right, there will be nothing traveling to the left on the right hand or on the right hand side of the barrier. So in that case, we can set b prime to be 0. So this removes an unknown from our equation. So this is for b prime is the equation coming over here when the ball is on the other side. So when we are writing, so imagine this is something very carefully you have to imagine. We have written equation for movement. We wrote equations for the on the right hand side of the barrier. We so if ball has come out from left hand side to right hand side, ball is moving to the right, that is along the positive x-axis. So there is no movement on towards the negative x-axis, so the second component coefficient must be 0. So RHS of the barrier, then when we are writing this, psi is equal to what, a prime e to the power I k x, okay, plus b prime e to the power minus I k x. This is what we were writing on the for the right hand side of the barrier. But there's nothing like this. I told you that e to the power ikx represents the motion along negative x-axis. This is for negative x, okay, minus x direction. So this is representing a motion of along minus x direction. So motion along that part. But imagine a ball has been thrown, it crosses the barrier from the left hand side, it goes through the barrier, comes out of the barrier, continues its motions. So it is only traveling in plus x direction. So we can safely assume that b prime, which we are saying, we can set it to 0. Okay, but we when we are looking at the equation 1 of the toward the left hand side of the barrier, we cannot set b is equal to 0 because the particle also gets reflected back. A portion of the wave gets reflected back, and there is a component of negative x. So negative x motion along the negative x direction is still there because of the reflected wave. So just we have seen that. So this particular thing कहाँ गया? हाँ ये. So because of this reflected part of the wave, there is motion along negative x direction. The reflected wave is showing negative x direction. This is the incident wave showing a positive x direction. So it has both the components, and when it has both the components, a is finite, b is also finite, so b cannot be set to 0. We cannot set b to 0. That is the only point that I was making through this on this slide. So we cannot set b to 0. There is a reflected portion going back in the negative x direction, and so the situation will be like this. So the proportionality, so the situation, we have b prime, we have set to 0. So now probability that particle is traveling to the right on the left of the barrier towards positive x is proportional to square modulus of a. Okay, the first equation we wrote for the motion of the particle. The probability that particle is traveling to the right on the right hand side of the barrier towards positive x again is a prime square from the laws of quantum mechanics that we have just learned. The probability, we know that it is coefficient that plays a big role of each of the contributing functions. And so the ratio of these two probabilities, left hand side of the barrier but traveling to the right in the positive x direction, and the right hand side of the barrier but traveling to the right, positive x direction. So positive x direction before the hitting the barrier, positive x direction after coming out of the barrier. Take this ratio square modulus, and this is known as transmission probability. What is the probability that particle will appear on the other side? Transmission probability of the particle. So this is what we T can be defined. It is simple through calculations. Kappa L. So the probability ratio, if it is worked out, it will give you something like this. So kappa L minus e to the power minus kappa L square, and this epsilon is coming up. This is epsilon is the ratio of E by V, energy of the particle, and V is the potential barrier, and T is capital T is the transmission probability that we have just indicated here. So for wide barrier, if the length is high, wide barrier means kappa L is much greater than 1. In that situation, the denominator is 1 is kappa L is much greater than 1. So in that case, for wide barrier, you have only 16. This this is 1 by, so this is a inverse, so it is 1 by this. So only term left out is, if it will be almost equal, so you can the other terms can be just neglected, and you are left with 16 epsilon 1 minus epsilon e to the power 2 kappa L. So the thing is that transmission probability for passage through barrier. So look at this. The first graph is incident energy E by V ratio and the transmission probability. So, and this the second graph is also of incident this thing, but it is for greater than 1. When so this is for E less than V and E greater than V. Both cases are presented. The particle has less energy to cross the barrier, classically forbidden, but the probability, you can see, it has finite. It is going on as E by E ratio increases, the transmission probability increases, and you can see here it is up to 0.5 50% probability. So this means at this point you have 50% probability of particle coming out, appearing on the other side. In this is to be interpreted as 20% probability at this point when E is equal to, so when it is written as 1, this means E is equal to V, or E by V is 1. So at this point you can see when it is equal, you have highest probability 50%, yes, and classically what you see, what you also see, so you can see classically it was forbidden, but you have even if energy is less, you can see that it is having a finite probability of getting out. And on the other side you see, if the energy is greater than V, so classically you should be, total of the ball should appear on the other side. Okay, when kinetic energy is much greater than the potential barrier, but that is not happening. So the transmission probability is less than, when it is E is greater than V, the probability is still less than 1. Probability is less than 1. This is also unexpected. It should have been 1. Classical, from classical point of view, it has probability is less than 1. This is an important point to see, and it only touches 1 when you have E by V ratio much greater, and that is also, so that it is rare to see that. So the curves level with this is the value of this thing. So uh, so this is the values are, it is the length of the box, mass that we can be taken into picture. So three curves that you see. So we are finding that when T's transmission probability is greater than 0 for E is less than V, whereas classically it should have been 0. And we also see that we can also see that when E is greater than V, मतलब बॉल के पास सफिशिएंट एनर्जी है हिल को क्लाइंब करने का, लेकिन तब भी वो 100% उस साइड नहीं आ रहा है. T would be 1 classically, but it is not happening. You can see the probability is still less than that. So this is the difference that we are seeing. So for higher probabilities, wide barriers, when kappa L is much greater than 1, the equation is simplified. So transmission probability decreases if the length increases, length of the barrier increases, or you can say the thickness of the barrier increases. The L large, L becomes large, probability will decrease. Transmission probability will go on decreasing. If the mass increases, it also depends on mass. So if the mass increases, again the probability decreases. So you can see a heavy particle, a lighter particle. The green one is for lighter particle. See, both are hitting the barrier with this with the same amplitude for both. Just a minute. So same amplitude, but finally you can see the lighter particle has a greater probability of coming out. It decay is slower and it can come out with a smaller amplitude. But heavier particle decay is very sharp, and within the uh, it has gone to zero. The amplitude has gone to zero. Particle has not come out. So lighter particle. So transmission probability decreases exponentially with thickness uh, of L, or the mass with a m to the power half with a dependence of this. So heavy particle, the decay is rapid. Within the barrier it is going to zero. For lighter particle, you can see that it is slower decay and it is coming out with having a smaller amplitude of oscillation. So lighter particle, greater tunneling probability, and so it is for electrons, protons. So electron is lighter than proton, so you can expect it to be more significant. So when what the discussion, the essence of the discussion is that electron, lighter particle is what? Electron. Heavier particle is what? Proton. Okay, so a proton or a H plus, which you acid base reaction. So there is lies the implication. An electron is likely to be more likely to be appear outside, can has greater transmission probability. It will appear, chances of appearing on the other side of the barrier is large for lighter particles such as electrons, and less for a proton or any other particle. So any two particles, when you compare the situation will be like that. And these effects are quite can be seen in chemistry as well as in physics or any other things. So this is a so ability of protons tunneling is also seen in transfer of proton from acid to base. So there also this is sometimes seen. We can interpret how the enzyme catalysis and all this can be explained in form of tunneling of the protons between acidic and basic groups. In a protein you have a lot of moieties which are, उसमें amino acid जो होता है उसमें दोनों ग्रुप होते हैं. You have amino acid is composed of uh, NH2, also COH. So carboxyl acidic basic groups are there, and tunneling of protons do occur in such cases. And you also have a tunneling phenomena occurring between when you have electron transfer reactions between at the electrodes. So and the most important part of this is that based on this tunneling, you can expect a tunneling current sometimes, and based on that we have there's a technique developed which is called scanning tunneling microscopy. The instrument is called scanning tunneling microscope, which can give you an image as precise as for an atom. So based on that tunneling current, the electrons is coming out, tunnels through the barrier, and you will get a current because of that. And that tunneling current can be used to get an image. So this is just I'm not going into the details of this, but you can, so it is a tip which probes the surface, and you can get, so this is a image of the cesium atom, the image, the bumps that you see. So this is just to give you an idea how important it is. ऐसा नहीं है कि ये सब सिर्फ एकेडमिक इंटरेस्ट के लिए वी आर लर्निंग दिस थिंग्स, कि एक टनलिंग भी होता है, टनलिंग का एक इम्पैक्ट है. यू कैन सी इन आवर lives it is happening in our body. In case of enzyme catalysis, it is there's microscope that has been designed to image an atom just like this cesium atom on the surface of gallium arsenide. Okay, so that brings us to the end of this, and